we've got a worked example looking at kinetic energy in collisions. Now, it's really important here that although you see this kinetic energy, what some people sometimes do is launch into a calculation involving kinetic energy before and after. We don't know before we do anything whether or not kinetic energy is conserved. But what we do know is in all collisions, momentum is conserved. So we start using that fact. We use the conservation of momentum to work out all the velocities. Then once we've got all the velocities, we can look at the kinetic energies involved and see, is it the same before and after? Okay, is it elastic or inelastic? Now it has actually told us here it's inelastic, but we've got to show by calculation, which means we've got to calculate kinetic energy before and after. So just like the standard momentum calculations that you've been doing, make clear your direction. Momentum before the collision for car A, and for car B it's negative because it's going in the opposite direction. So we've got the total momentum before. We know that they collide head-on, lock together and move off together. So the after looks like this. Treat them as one object with a combined mass of 2,200 and moving with a velocity v. We don't yet know what that is. So we know the total momentum after the collision though can be written as 2,200 times v. And because of conservation of momentum, that must equal the total momentum before. So 3,000 must equal 2,200 times v. And therefore we get that the velocity of the cars after the collision is 1.36 meters per second to the right. Okay, got to include the direction. So that's just a standard conservation of momentum problem. I'm going through that quite quickly because you've done quite a few of them now. Now let's consider the kinetic energy. So what do? We can't do a single combined calculation of kinetic energy before. We've just got to consider each car on its own and apply a half mv squared to each individual object. So we do that for the first car and for the second, and notice we don't actually need to put in the minus there, but even if we did, which is probably better form to be honest, when you square it, it will become positive. So energy is a scalar quantity, it doesn't matter what direction it's going in. So we just have to add the two values to get the total kinetic energy before the collision. We use the velocity we've worked out to get the value for the total kinetic energy after the collision, a half mv squared for that combined mass. Now we can join them together. And therefore we've showed that the kinetic energy is not the same before and after, and we've proven that it's an inelastic collision. In any show that question, it's important that you start with formulas and work towards the answer, and don't start with the answer and work backwards, because that's not accepted in the marking schemes.